Yes, get started. I'll give a brief introduction first, and really glad to have the second time in person seminar series this semester, and I'm very glad we have visitors from MIT, professors from the Keith's lab. So we have three visitors today, Sewon, OJ, and David. So yeah. I assume they're going to kind of co-present a little bit about what their work at MIT, and I think many of you probably know Sunbase Lab, and I would say one of the most hardcore hardware local motion groups, and I just learned from the lab, they don't use any other commercial platform. Everything is built from scratch internally from the lab. So this is still very impressive, especially given the recent trend, what happens to humanoid these days. Okay, good. So I think we will talk a little bit of, I guess, a mixture of RL and parallelized model based. So it's going to be like a hybrid model based and learning based approach. I think which fits very well to the audience here today. So with that, I'll say welcome and. Let's get started. Okay. All right. Thank you.
Thank you so much. Today we're going to be talking about our, our research, our kind of trend in lab. Professor Kim, he likes to still incorporate structure, inductive bias, and model-based kind of things into these RL pipelines. And I think, throughout this presentation, please feel free to stop me, ask questions. If we can make it kind of more discussion-based, that would really help me as well. With that, we'll get going. Today we'll be presenting to the LiDAR group and other people about our work. So let's just jump in. So as a brief background, Professor Zhao did a meeting is being recorded. That's fine. Great. To jump into this is our background, MIT Robotics Lab. As Professor Zhao said, a lot of stuff we do really focuses on hardware. Like we're very close to hardware. We would like you to not ask us hardware questions because we're not hardware people, but we can talk. Actually, David probably answer all of those questions. But even so, as control engineers and as RL, whatever kind of control have you, we stay very close to the low level hardware, which means we need to fix and interact with it. And we have a big focus on having very highly dynamic systems. Like here's our ping pong robot over here. Our mini cheetah, our humanoid platform walking around. A lot of these platforms we try and design custom from scratch, and having to control that and not having that layer of nice industry to be able to smooth out the bugs makes it so you really have to get familiar with what you're working with, bugs and all. So for the first part of our talk, I'm going to talk a little bit about my work called Kusadi, which is about how we parallelize on the GPU symbolic expressions and how we can extend this to things like model-based control. So let's jump in. In general, in the robotics community, I would say, especially among the more kind of traditional roboticists, there's a big trend towards trying to combine these two approaches, like model-based approaches and learning-based approaches. We have our classical NPC, linear inverted pendulum, like zero moment point, those kind of traditional techniques we have studied over the last 20 years before. Over the last 20 years, and the more modern stuff, where we have RL diffusion and these kind of things coming in. And just the point here we want to take away is there's a lot of interesting things trying to combine these works. How do we combine them intelligently? How can we structure these together in a way that we have robots that are more robust, reliable, etc.? But the problem is, even just combining this at like a base level of how to implement this is already a challenge. To effectively parallelize computations across the batches and scales we need for reinforcement learning, we generally train with thousands of robots at the same time, which means all the model-based algorithms we use need to scale for thousands of robots at the same time. So when we think about the just overhead and bookkeeping that's required to do this kind of thing, it's already overwhelming. We have costly overhead from transferring and copying data between the CPU and the GPU. We have to keep algorithmic bookkeeping of each environment, like algorithm 1 this corresponds to this environment in this robot, and then algorithm X corresponds to this other robot in environment 50 that's about to fail. How do we keep track of all these things at the same time? And this is a high barrier to entry. I had to learn a lot of CUDA and bare metal GPU programming. That's not something that a roboticist should have to know to be able to kind of access these algorithms. And so that's kind of what our work is focusing on. Right now, we see this kind of trend where you have batch computational efficiency. How efficiently can you compute many things at the same time? And this is how hard it is to implement, roughly speaking. So we can have our naive for loop, where over whatever 4,000 environments that we train our with, we just put a for loop, compute a symbolic expression for every single one. Then we could do some clever parallelization. We could use huge clusters and lots of money. You could also go straight to the GPU. But like I said, ideally, we don't want to have people need to know this to be able to implement these kind of algorithms. And so that's what the focus of our work today will be. Kusadi. Cool. So what I want to start with is by talking a little bit about the baseline framework, which is called CUSADI. And some of you guys might have used this for optimal control, optimization, dynamic programming, whatever. What's very useful about this library is that a lot of dynamics and controllers are formulated in CUSADI. And the way CUSADI expressions are written is like this. When I have a function sine x plus x squared as an example, it's represented in the code as this graph, where we have these atomic expressions, atomic operations that define everything. So we follow the chain of the computations here. We sign this expression, then we also sum these two together, the value of x and sine of x, as we see it here. Then we put that through a square operator, and then that's our final function. So, symbolically, it's really nice to have because now we can do things like differentiate it. We can add values to it. We can subtract values from it. Things like SymPy or Mathematica also have this kind of feature, and this is how CUSADI does it. But the main idea we want to do here is instead of having scalar operations for each of these, we can actually vectorize these operations individually. So here I'm transitioning to talking a little bit about how the GPU works, and computation. So a vectorized operation is exactly what it sounds like. Instead of operating a sign on a single scalar, we just apply a sign on an entire batch, a huge array of scalar values. And so with this single operation, all of these computations are done in parallel on the GPU, and so we get all these array of outputs doing a single operation across all. And so when we do this, we scale very well with the number of threads we have. Just for reference, a CPU typically has 10 to 20 threads, whereas a GPU has up to thousands, which is why this scales really well for high-dimensional data. So things like graphics processing, parallel simulation, and Isaac Lab, and that kind of thing, this is what it takes advantage of, because we can do this vectorized math. Yeah, question.
I think people online said there's an mute.
I'll mute myself. Let's
You can mute here.
okay. I'll mute this computer. That's fine. Thank you. Cool. And so our main takeaway is this, like, let's take our symbolic expression here, and for each of these expressions, let's just apply the vectorized version of these across each of the inputs that we have. So we have, 4,000 x's that we want to apply this function on, and now we have the vectorized version of this whole function. And so we get a tensor of outputs that is this function applied to as many inputs as we care about. And so this is just, GPU evaluating it. In mass, simultaneously, we're computing this function wholesale. And so each of these operations, the pluses, the minus, square, sine, each of these I can define a single GPU kernel for, like a GPU code for, and I can simply just replace, if CUSADI is telling me I need to do this set of operations in this order, correspond the GPU operations accordingly. And now I have a batch operation across all of these. And so we do some code gen, compile this. This fundamental, like low-level details of this, we can discuss offline if you guys are curious, but that's kind of like the high-level architecture of what's going on. Okay, cool. So let's quickly do a benchmark of how efficient is this? How good is this? What we do here is we compare the speed up of our work, CUSADI, relative to the most naive CPU implementation. Like I have some sort of function I want to run, and I'm doing a massive just CPU for loop of like whatever, however much batches I want to evaluate on. So I have 500 environments. I'm going to do a naive CPU for loop. How much speed up do we get? And these are the results that we see. So generally speaking, we have a pretty high speed up, especially for simpler functions. A simpler function is like how many instructions we have, how complex that, and how long that function gets. And this is how our scaling looks. But this graph on the left does not include the time that it takes to copy the data from the CPU to the GPU. And this is where a lot of the overhead is taken. If we include that time, and we also include how much time it takes to copy the data, to compute something on the CPU, copy to the GPU, and copy it back, which is what would be required for some sort of RL model-based interface, this is actually the speed up that we see. And we see that the CPU scaling really starts to decrease because you have to copy this data, and that overhead is so substantial. Yeah, so our speedups are solid. And it's very important to keep keep the computations on the same device for efficiency. That way you don't lose any time and memory trying to copy data back and forth when it's not needed, if you can do all your computations just on the GPU and cut this out entirely. Cool. Yeah, question?
So when you increase the number of instructions,
yeah,
you start to see the less scale up from CPU to GPU. I think when you look at the graph, right, you can see the speed up when you increase the number of instructions. I guess the number of instructions for the CUSADI, right?
Yes.
So why is that speed up?
Oh, good question. Yeah. So the question was about basically this trend downwards. Why is it that as we increase the number of instructions, as our function gets more complex, our speed up decreases? So this is because of just the nature of GPU programming. Essentially, I think you guys can think of a GPU as like, you have like 200 elevators all going up very, very slowly, versus a CPU GPU is like you have two elevators that are extremely quick. And so where that slowdown starts to happen as you have more instructions is because the ALUs, the arithmetic logic units of that processor, are much slower on the GPU. So when you need to do many sequential functions, the GPU is not as fast as a CPU. Yeah, you understand. But essentially, imagine like a big queue of people trying to get up a escalator at the same time. You could either have 200 people go up like a very, very slow, wide set of elevators versus a very quick set of like narrow escalators. That's the analogy we want to think about. Cool. Thank you for the question. All right. So I've talked a little bit about, I've talked a lot about these functions and GPUs and parallelizing, like what is the use cases of this? And so let's talk a little bit about toy examples of what we can do here. So a Casati expression, I can express any kind of symbolic expression. So that could be the dynamics of a system. It could be sine x plus x squared, whatever. In this case, let's just write the dynamics of a quadcopter, just represented in this form symbolically. And because it's symbolic written in Casati, that means I can parallelize it on cuSATI for the GPU across as many environments as I care about. So immediately, if we can write the dynamics like this, I have a parallel simulator. This is just code gen on bare metal GPU, and I have something that's very efficient and very quick. And so if we have this parallel simulator, what can we do with it? Well, as with Isaac Lab and all these kind of parallel MJ Lab, all these RL environments, we have an environment for reinforcement learning. We could do things like sampling-based control, where we can do bunches of these rollouts very efficiently at the same time. And we can do things like region of traction and stability sweeps, kind of like big high-dimensional scale sweeps that are hard to accomplish without this parallelization. So we're going to talk a little bit about this kind of toy example, and let's see what happens. In this case, what we did is we expressed the dynamics of the quadcopter, and we attached an LQR controller to it. Again, all of this was expressed symbolically in Casati. I can write Casati LQR, if you can abstract it away in your mind like that. And I have a function that spits out what the dynamics would be given a LQR controller that's trying to stabilize here. And so let's see what happens when we perturb it. Like I'm going to push it linearly and perturb it angularly around this nominal state. And let's ask some questions about our controller. I want to know what are the bounds and the limits of this controller. And so what we do is we initialize it here, and we vary like the maximum thrust, the force that the quadcopter can produce from this. And we ask, from what states can it return from what states will it just spiral away into infinity? And we can do this very efficiently in cuSATI. And here's what our space looks like. So if our maximum force is 15 unit meters, we have this interesting shape. And this is the range of impulses that we can recover from initially. We've characterized our LQR controller, our region of attraction, very trivially with this toy problem. And we see that as we decrease our force limit, our region of attraction also shrinks in this pretty non-intuitive kind of flame-shaped pattern, which is cool to see. But like I said, this is a toy example. So let's go through another one. Let's ask a different question, which is instead of studying the response of a fixed controller, let's see what happens when we want to study the parameters of that controller. I have an LQR controller and I know I want it, but I have a question of like, how does the trajectory that I get depend on the parameters of that system? That's not something that's easy to compute, especially, you'd have to do some differentiability. You could sample it en masse and in a big for loop. But with this parallelization tool, we can actually study this pretty thoroughly. So in this case, let's look at two things, the LQR weights and the system parameter, in this case, the mass of the quadcopter. I'm going to initialize the quadcopter from various positions in XY location. I have an LQR controller that brings it, but I'm going to instead vary the weights of that system. And what does our trajectory look like? And here's what they look like. So here we vary the QX, the X weight of that LQR controller, started from 3 different initial positions. And we get this really nice blend, the sweep of what the trajectory would look like. And so we see somewhere in between the extreme of 20 to the minimum of 1, we have a nice, like, critically damped path. But, if we overweight it, we're going to overshoot that. If we underweight it, we're going to take a long time to rise there. And we have this nice view of what we want to do. Similarly, and I think a little less intuitively, we have here the weighting of the control input R as a single scalar. As we scale this up and down, we see how these behaviors can become very different. And they almost like do this overlapping thing. And the trajectories can change based on what that value of R is. But from a high-level perspective, we can do these big sweeps and see for system design, for parameter tuning, whatever, what the behavior of our controller is. And likewise, here's the same for mass. Yeah. Cool. Any questions here?
Just make sure I understand the setup. Like this is you use cuSATI, right?
Yes.
So this help you? What this help you? Like help you to sweep the parameters to generate the results? Like
Yeah. Exactly. So we can do all this in parallel. Just a toy example of like, if we had started the quadcopter from a location and we have an LQR controller, let's sweep across a parameter of our controller. Like if you thought this was MPC, this could be one of the weights of MPC. In this case, this is the input weighting of an LQR controller. Yeah. And so we see like when R is very high, this is the path we would take from this, yeah, for the quadcopter. And if R is very low, this is the path we would take. Yeah. So just high level, it can provide you like a pretty comprehensive overview of, what are we doing? But like I said, these are pretty like simple toy examples, which you could do with a for loop. I just want to illustrate some like use cases of parallelization in general and scaling up our controllers and scaling up our data. Yeah. To kind of wrap up at least this section about parallelization and why it could be useful. The whole point of why we might want to bring GPU parallelization to modern learning paradigms is these are kind of the emphasizing points that we want to talk about, which is let's try not to rely on end-to-end architectures as much, but using our prior model-based knowledge that we've spent a lot of time building up, can we somehow embed interpretable, debuggable, composable units into these data-driven architectures so we can still maintain some sense of engineering into our controllers. So in terms of just like bigger picture visions, in terms of what we could do with Kusadi, there's speed ups and potential for improvements here. I think what we're going to talk about today a little bit is learning and control, how we can use these parallelized model-based architectures as part of the learning loop, and also more broad high-dimensional applications we could think about too. Like we've kind of waved away, and you guys have probably learned about dynamic programming and value iteration. Yeah, cursive dimensionality, it's kind of hard to scale. But honestly, our compute has increased so much since I took that class where I learned about it. And I'm curious to see if we can tackle those kind of problems again with kind of the scaling up of GPUs, because they're getting bigger and bigger and bigger every year with more and more threads. Like, is this something we should look at again? And that would be very interesting. Or like a single rigid body model system, can we do value iteration and really find a globally optimal value function? That would be an interesting question. Are we at that level of scaling yet? But with that, I'm going to turn it over to our second part of our talk, which is how we actually structure controllers with these model-based priors, leveraging Kusadi. And I'll turn it over to Hojay at this point.
All right. Here's a question.
Oh, sorry. Yeah.
When you like translate the study, is there any machine issues?
That's a great question. So the question was about whether there's any floating point precision issues when I convert from Kusadi to Kusadi. This is kind of like a tool level discussion, but basically I give users the option to have the precision be in floating point or double precision. I think it's actually an interesting case that some controllers depend on the double precision solve, and some seem to be fine with floating point. Generally speaking, GPUs are much, much faster with floating point, and a lot of like, especially LLM and VLM architectures actually go down to like 16-bit precision to compute even faster. I would say like, high level precision matters, and it's an option which one you need, and you can customize that as you need. Yeah. Yeah, float is fine. There was one case I saw where double seemed to really have a difference, which was in, solving an MPC problem, but I want to talk about that. I will talk about that a little bit downstream. Yeah.
All right. If you don't have any more questions, I'll move on. Yes. So hello again. My name is Hojay. I'm a third-year PhD student working in the biomedical robotics lab again. I'd like to thank Professor for a kind introduction. It's a nice introduction about the Kusadi tool. So the presentation that I will give today will be about a case study of how to integrate model-based prior with reinforcement learning policy for humanoid locomotion task, especially the leveraging the Kusadi tool that we just introduced. And the title of the work is Learning Humanoid Arm Motion via Centroidal Momentum Regularized Multi-Agent Reinforcement Learning. Its RIL submission will be presented in ICRA, hopefully to see some of you guys over there as well. So because the focus of the presentation is humanoid and a lot of you are interested in humanoid, let's briefly talk about the humanoid robot itself. It's everywhere in the headline these days, and I say the primary strength lies in the generality for many applications for the humanoid possibly has. And because especially they share the form of the human as we are, they're uniquely adaptable to challenging terrains like the human-centric environments, basically built for us. And with dexterous human, like anthropomorphic hands, they can also take on intricate and dexterous tasks, such as grasping and like folding laundry and stuff. And their physical structure allows for natural and helpful interaction with the people. However, I would say most of the tasks that you see in this video are achieved through direct imitation of the human data or manual teleoperations or very specific handcrafted task rewards, which could potentially limit the functionality of the robot. And in this work, in our work, we like to take a slightly different approach, which is we try to aim to integrate the insights from the human behavior just enough to induce the meaningful and autonomous behavior. So looking back at how human moves, this is kind of a spirit of biomimetics part of our lab. We can notice that people are naturally swinging their arms during walking, running, or jumping. And a key finding from the biomechanics studies shows that these arm swings reduce the total angular momentum of the body. And in turns, it lowers the ground reaction moment that the contact foot needs to generate. And this shows that the arms are not just the passive appendages as a vestigial relic, but it actually plays an important role and improves the stability when we locomote. And the further studies of biomechanics also shows that by comparing like different scenarios like this, normal cases, and sometimes they bound the human's hand and like make the human like walk in phase, which is anti-normal, and compare, as you can see, in a normal case, it lowers it achieves the minimum whole body angular momentum as well as the vertical ground reaction moment around the contact foot, which is connected to the stability of the locomotion. So with these findings, we can also think about the similar concept in the robotics community, which is centroidal momentum and dynamics. And it has been extensively studied in robotics community, which can be used as a solid theoretical foundation that connects the findings from the human biomechanics to the robots that we're using. This is our MIT humanoid that we're using. And especially you can the function A of G, which is the formation from the mass matrix, can be computed. We derive it using the Pinocchio, and we can parallelize using the Kusari tool. And this is basically where we use the Kusari to parallelize the model-based priors. So drawing up on the findings from biomechanical studies, in this work, we aim to learn the coordinated whole body motion via momentum-guided RL using with the following contribution. First, we designed the centroidal angular momentum. CAM stands for centroidal angular momentum rewards based on biomechanical studies, as you saw it before. It guides the emergence of natural arm swing motion for stable locomotion and also effective push recovery when you're under the unexpected external perturbations. And we choose to, we can achieve this natural arm motion, especially by adopting this multi-agent reinforcement learning framework that separates the actor-critic network for the arm part and the leg part, because their role can be distinctively separated and in some specially trained manner called centralized, trained centrally, but executed in decentralized manner. We'll explain later. And we also validate our methodology in our MIT humanoid platform in simulation and hardware. So now let's talk about the actual methodology, how we achieve this. So this is the overview of the framework. I would say the first thing that I'd like to point out is that we model the arms and legs as a separate agent with its own actor-critic network. The arm basically takes its own observation, which is the arm parts, and the leg takes the leg parts, while they share the base states and the central angular momentum. So we leverage the central angular momentum to connect those two separated actor-critic networks. And also we use the centralized training and decentralized execution manner, which means that the critic here, although the actor takes its own observation, the critic takes the whole observation, meaning it's trained centralized. But we don't use the critic during the execution, so we can use it. We can actually take advantage of this fact. Yes. So in humanoid robotics field, actually, when I did the literature review, this multi-agent framework has not been really widely used. So let's briefly discuss why we adopt this framework. So by separating the arm and leg agent, I put it here again, we can have a separate reward group for localized objectives, because if you put it in a single agent, if the rewards are conflicting each other, their gradients can affect each other so that the objectives cannot be really well achieved. But by separating this reward group, we can have the gradient update independently so that they're not conflicting each other. So we further adopt decentralized critic part to observe the holistic information about the system and the task, which will help addressing one of the problem if in the multi-agent settings, because if you have multi-agents with a similar task, when the task succeed or fail, it's sometimes get difficult to who to blame or who to credit it. So we call it the credit assignment problem. And by having this critic observing the holistic information, it helps addressing this the credit assignment problem. So yes.
You have two of them.
Yes, so centralized training. So we use the critic only during the training, right? We use the actor for the execution when we actually run it. So if you see the critic is observing, I put it at a dotted line, is actually see everything here, meaning the centralized. You can also like a global observation. Yeah, but the CTD or centralized training is commonly used term in the moral society, like so.
Question. So you separate the leg and arm.
Yes.
So do you like to share the observation to both for example for the arm policy for training, do you consider like the leg observation to the arm policy and to consider the arm to the leg policy?
Yeah, so that's basically the idea here. So for instance, for arm, it doesn't see the leg specific information, but you only give the centroidal angular momentum information so that we can interpret centroidal angular momentum as a kind of latent information about your counterpart. So say if you are like pulling the rod each other, you don't really need to how your component is actually like moving your arms and legs, but you just need to understand like the tension in the rod. So that kind of intermediate enough information in low dimension is sharing this central angular momentum part. Yes.
So here you have the two of the critic.
Yeah.
Do you consider using like one actor and two critic? Each critic is spoken upward.
One actor, two critic.
Yeah, some people actually do like multi-critic plus one actor. I'm curious like how this application is.
I would say if you use the single critic, a single actor. Yes. So we didn't really do the ablation study on single actor multi-critic, but we did ablation study on the later on single critic, single actor, and which works much less, basically because we think that the gradients are conflicting each other, and if you plot the task reward, is much less than what you can achieve with the separating the policy. So I think with the single actor, the gradient will like kind of confuse, like because the reward itself is just a scalar value, right? So it will like lumped up sum will make the gradient not really clear what the objective is.
I think having two separate critics
Yes.
is different from summing the both.
Yes, so I think having separate critic might help address this problem than just single critic, but I'm not sure about like I still think that having separate actor is an important part, as they're the one being executed during the execution and will be actually used for the execution, and then the gradient will be flowed. Yes, we can discuss more later. Yeah. Any more questions before I move on? Okay, so let's briefly discuss the detail of the framework. So as I said, the actor, so actors are separated, whereas the critics are centralized. So the leg part will observe the leg join information as well as the command and the face, whereas the arm part observes the arm part and then the desired central angular momentum. And then they share the base states, and this central angular momentum will act as a latent information to communicate of each other. And this critic will observe everything, and the action will be just a desired joint position target for each network. And then we run the joint PD controller under the hood in a much higher frequency. Now the important part is the separating the reward group. We think that the leg's primary role is to keep the stability for the locomotion and also following the velocity command that we are giving as a command. So we basically have the velocity tracking part and the context schedule and bunch of the regularization parts to keep them in the physical constraints. Whereas the role of the arm is to assist the locomotion by swinging the arms so that to reduce the central angular momentum and recover from the external perturbation. So using this central angular momentum that we parallelize with the Kusadi, we can have this vertical CAEM tracking part and the damping part. So their roles are clearly differentiated, that the role of the leg is to track the velocity, whereas the arm is to stabilize the locomotion. Yes. So now we have all the lever. Now we can turn the, right? Yes.
To go back to this, what do you mean by vertical central angular momentum? What do you mean vertical?
Yes, so the vertical like z-axis. Yes. So if you think like we swing the leg, it generates this, like as it moves, it generates this vertical angular momentum.
It's not the DM is the angular part, not the linear part.
Yes, yeah, angular part. So the momentum, central momentum is actually six dimension. This is only the sixth part. Like we don't consider the linear part, only the angular part, omega x, omega y, omega z, and it is omega z part in the momentum. Yeah. Yes, yeah, you're taking it.
And then I think the K hat is in the previous slide you show it's from the arm part.
Yes.
I assume it's from the human motion analysis.
So this I think I didn't write it. So this is derived from the velocity tracking part. So this V hat is x like linear xy part and a yaw velocity. And then we can multiply this part to the centroidal momentum matrix to deduce the desired centroidal momentum.
Yes. So I guess my question is when you derive this centroidal matrix, it's a matrix of the whole body state Q, right?
Yes.
But I think now this K hat seems only from the arm. Is that right? The reference you're trying to track is from the arm.
No, because this is the AG, AQ.
Yeah. This is used to calculate the actual centroidal momentum, right?
Yes, the desired centroidal momentum.
Is it just from the arm part or
the whole part? Because because this AG is 6 by the whole joint.
Okay.
Yeah. Okay. Yes. So now we can turn the crank and then let's see the result. So we first train our policy in the Isaac Lab physics simulator. This is Isaac Lab physics simulator. And the resulting behavior shows a natural arm-looking motions that resembles the human motions. And as the biomechanics study suggests, our approach results in much less fluctuation, which is our solid black line, and our comparison is the light gray line. So if you compare, we are comparing walking with this arm bounded versus actually like walking using our policy. which result in much less fluctuation of the vertical centroidal angular momentum. And we further decompose this black solid line into three components because centroidal angular momentum as a whole can be attributed by the part of the arm part and part of the base and part of the leg. And you can see that legs and the arms, which is blue and red line, are exactly out of phase. They're canceling the fluctuation, leading to like more stable locomotions. And the effect of the arm swing becomes clear in the vertical ground reaction moment plot. So the vertical reaction moment is on the foot in the contact. You can plot the forces of the heel and toe, because now we're modeling is just heel and toe 2-point contact. And you can multiply it with the moment arm. So R cross F, this is the actual force. So if you multiply the R cross F or the center of pressure, you can collect this bunch of data of the distribution of the vertical ground reaction moment. And as you can see, and as is actually consistent with the biomechanics studies, our cases with natural arm motion, normal arm motion, its distribution is much lower and its peak vertical ground reaction moment, or GRM, is much lower. Yes.
Is the without cam baseline on your RL controller without apply cam reward?
Yes, this is without the reward that I showed in the arm part, but still has the regularization term to regularize like excessive arm motion. So here, because the velocity is pretty low, you can't see the arm motion, but it actually like swinging, whereas this is like perfectly fixed. Yes.
And the arm, like just to do the flywheel tap, is that possible?
For this case?
Like this type of.
Yeah, I mean it is possible, but it just learned to, I guess because of the only the joint regularization term, it just learned to like try to be stabilized around the 0 radian.
Something we've consistently observed when we allow the arms to be completely free without any kind of joint regularization is it often learns to keep the arms up in the air like this, kind of tucked and bent. Our theory is that self-collision termination penalties is why it likes to keep its arms up here, so that the arm is far away from the body and won't touch anything.
Yeah.
But without any kind of regularization, it always does some goofy thing up here.
Yes. So we remove that to avoid that weird motion. We still leave the regularization part. Okay. So we also test our policy on the actual MIT humanoid. I don't know if you see our humanoid. This is our humanoid that our previous PhD students have built over the past 3-4 years. So it's not as nice as Jeon robot, but it's still cool. So this is the treadmill that we are running, 1.3 meter per second. I was giving the velocity command. It's still tracked pretty well, and you can also see the arm motion naturally coming out from our policy. Yes.
What if you lose the joint regulation term? Joint regulation, reward for your arm a little bit, then would it?
Yes. So that comes down to like a tuning part. So in extreme case, if you remove the joint regularization term, as Hwan said, like really go really crazy and like it's jittery a lot. So we had to tune it in a reasonable range, but not dominating. Yes. Okay. Thanks for the questions. So now we apply external perturbation, because one of the contribution is that using this reward setting with the model-based prior with this central angular momentum idea, it can recover from the push recovery very well. So what emerges is the coordinate arm motion that plays a critical role in stabilizing the balance after the disturbance. As you can see, oops. Oh, the video is playing. Oh, there, but yeah. So here I am pushing the robot. I press key, pushing the robot in the base. So the base, the K dot, which is, because force is the time derivative of the moment, right? So I give force, which will make the base time rate of centroidal angular momentum oscillate. And this red line is also it's just the emergence of the arm motion. I didn't specify anything, but based on the reward of minimizing the central angular momentum, the arm motion here arise naturally to counteract the push the force external perturbations. So we further compare the recovery performance over the wide range of the torque range of disturbances, and then our approach with active arm motion shows significantly greater, which is the blue range here, that shows the capability, like larger capability of recovery than the fixed arm cases. So we also tested with the real hardware, so you can see that arm motion like naturally coming out. And this guy's blurred. Oh no. Oh. Yes, this guy is this guy. We had a lot of fun. And now our second contribution was about we adopted this multi-agent RL to achieve this nice emergence of arm motion. So we want to discuss, is the multi-agent RL really necessary and why we need like centralized training of the critic. So we first compare like lots of different things. So first I'd like to point out that as Jeon asked, or Zunovsky asked, if you use the single agent, this is how the motion looks like. So this is a task reward of velocity or total reward. And you can see that the yellow line is converging much less values and much slower because the rewards are conflicting each other and they got confused about like achieving the objectives. And the resulting motion is also a little weird. But you can see that the red line and blue line kind of overlapped is the centralized training versus decentralized training, which is comparing do we need a global observation for the critic, or can we just use the local observation as actor? So here we compare the variance of the advantage function. So the advantage function is used in the RL when you calculate the gradient descent, gradient value, you take the gradient of the advantage function, which is a kind of value functions. And the variance means that how reliable that gradient signal is. So the smaller the variance is, the less jittery the signal is, meaning that you can trust this gradient information much better. So by using the centralized training, by having the critic observe holistic information, we can have much lower variance, meaning the gradient information itself is more reliable to help the learning. And we also further try this on the uneven terrain. This is Isaac's lab environments with slope and stairs and uneven terrains. We also tested. This is like a minute of video, so we can just watch it. So this is also the same treadmill that we put a bunch of different uneven obstacles. And here you can see the arm motion, but arm motion is not that observable because the velocity itself is not that high. But like as you saw previously in the simulation, if you go really fast and it was really about to tripped over, you can see much bigger arm motions. So this is Hwan is pushing it. So try to yes, I can jump a little bit. And then we also tried on the single step, and the arm motions are coming out. And we also tested on the, yes, two steps cases, where you can see the arm motion are generating. Okay, yes.
It's a little hard to observe from video, but I wonder if you observe like this kind of aggressive arm motion, protective motion when the robot steps on a obstacle or steps down an obstacle. Probably arm motion might be needed in those cases. Did you observe that kind of aggressive
Like protective, what do you mean by like protective motion?
Like when it steps on.
Yeah.
If it steps down, then probably unexpectedly, then like there's a large momentum.
Yeah.
Triggered by the height difference.
Yeah.
So I believe arm should go like onward.
Yeah, that's true. So here we didn't really like make like tripped over too aggressively because as we discussed, the fixing it takes too long. So we try to be quite modest. And you can think of this tripping over because this robot is completely blind, is basically you can think of it same as like we are pushing ourselves. And when we pull the rubber, rub the string, it generates like big motions. So when the tripping over motion is like very big, the arm motion also will emerge large. Yes, please.
Do you go to the 35th slide?
35th.
Yes, it's
Yeah.
so I just was wondering like if the robot is symmetry, right?
Yes.
Like for example, in the
here.
the map for the fixed arm,
Yes.
it seems like this map is not like symmetry.
Yes.
Like between the center, right?
Yes.
I'm wondering what kind of
Yeah.
make this like asymmetrical behavior.
Yeah. I agree. So I would say, so this is one of the kind of reviewer says as well. I would say all the data are like resampled. So the sampling itself might not be like perfectly even, but I don't think that's explained it. I would say mainly the policy itself does not converge in a way that like both action respond exactly the same. So it's more of like a reward how the policy converges in the end.
Because sometimes also like during the RL training, even if like for example we use some motion reference guidance, sometimes we still could find like some for example the left leg and the right leg they are not very perfectly
exactly
symmetrical, right?
Yeah.
With some local
Yeah.
motion tasks.
Yeah.
So just
yeah,
wondering
I think that's a similar
there-
context to that the arm motion for the left perturbation case, the right perturbation did not train perfectly because also like during the training we call it a domain randomizer. We kind of push it, and that might not be exactly like 5 times left perturbation, 5 times right perturbation. So that kind of converged. You had a question?
Oh, yeah, I had a question. You earlier showed the videos where you're comparing this approach to, for example, not using this type of reward or regularization. I was wondering when you had to deploy in these environments where there is disturbances, do you have to retune again this reward, or is it like the same model that?
Yeah, this is all exactly the same model. Yeah, just a single model that does everything the video that I showed. Yes. So I explained this. So as a last, I'd like to summarize the takeaways of this the presentation. Is that the first the arm motion guided by the central angular momentum regularization reduces the vertical CAM and the vertical ground reaction moments, and as a result enhances the robustness and stabilize the locomotion. And also our multi-agent RL framework improves the overall task performance and stabilize the policy learning. But I'd like to also point out that the learning that we got from this project is not really restricted to the humanoid itself. So we actually are doing the a similar task with completely different platform. So, but we're not going to talk too much detail, but this is like current ongoing work with the manipulator work. This is also exactly the same multi-agent reinforcement learning framework with the arm part and a hand part. So the learning that we get if we know their roles are distinctively different, we can use the multi-agent RL, like about the global transportation of the arm parts and also local manipulations, and use that learning we did for a different platform as well. So stay tuned. If you're interested, I'd like to, yes.
Yeah, sorry, I had one quick question. I was just curious if you explored like different, it seems like you prescribe a context schedule as an input for the policies for a
Context.
particular gate.
Yeah.
Did you look at different gates? Because I feel like for some gates, you kind of do different things with your arms.
Yes, so the gate is kind of like 3 hertz, which is kind of, we found it stable for our morphology humanoid. And the focus of this work was not really about the gate schedule, so we didn't really dig into that. We just stick to 3 hertz. But I do agree that different gates will have a different motion, and also like the frequency and everything will be different. So the motion will probably different. Yeah. Yes. So if you don't have any further questions, I will pass it to.
Thank you. All right, cool. So to wrap up the talk, I want to talk about one other application of how we parallelize something model-based and how we, incorporate that into a learning architecture. And so this is probably going to be like the big push of my thesis. So feedback, criticism, questions, please let me know. Yeah. So we talked about the prior work, all of Hoji's stuff, and what we showed before is we can parallelize model-based stuff, model-based quantities, model-based controllers, etc. So let's really go all the way, the most complex model-based thing that at least I currently know, which is let's actually parallelize the MPC formula as well, the MPC computation, and have this in the loop as part of the RL training pipeline. So what we did here is this is a residual architecture. Let's have MPC be our core controller that is, agnostic to data, state distributions, whatever, and learn a small residual offset that can adapt and adjust those outputs of the MPC controller as needed and see what that architecture looks like. This was as minimal as possible to try and get clear results, and I'll be clear about what that means. But as I said, we use Kusadi, we parallelize the MPC controller, and this is kind of the framework and motivation that we have. We have this core planner, and we have this layer of corrective actions that hopefully can handle things like small disturbances and foot estimation and noise and that kind of thing that MPC can be susceptible to. So let's just start with basics. Here's my MPC controller with the predictions visualized as it's stepping, fixed gate controller. I can parameterize and tune like how high I want the foot to swing, like the contact sequence and how quickly it is. It's standard MPC controller. With SQP, I have lots of technical details about the nonlinear optimization that I'd love to talk about if you guys are interested, but I won't. That's for later. And yeah, let's just take the minimal set. We have this residual architecture. It's literally just added together. I have the MPC torques and then the RL torques. Let's sum them, smash them together with a small scaling factor and see what happens. And so this is our setup. Let's look at 3 controllers. Only our MPC, which obviously won't benefit from any kind of learning. The end-to-end RL only, and then the residual. And we choose a set of weights which are defined, a set of weights and rewards. These rewards are very minimal. There's no imitation going on. It's just purely linear velocity tracking, angular velocity tracking, regularization. And for all these 3, these rewards are kept exactly the same. And that's very key, just to see what the behavior looks like. And so once we train these policies, which takes a long time because of the parallelization, let's see what our rewards look like. And this is the converged behavior asymptotically. Blue is the end-to-end. I'm keeping this color scheme throughout. And the orange is the residual. They converge pretty close. Like in terms of absolute reward performance, we don't really see a massive difference. And in terms of the covered velocity capabilities, they also seem pretty similar. The MPC we notice is like, measurably worse. Makes sense. It's a model-based controller susceptible to noise and parameter mismatches. And that's what we see. So the rewards are all the same. The velocity capability and the tracking is all the same. Let's actually qualitatively see what this guy looks like. Again, here's our blue RL. And I'm sure if anyone's played with RL, you've seen this kind of behavior where it exploits the physics of the system. In contrast, let's look at our residual MPC here. This is the behavior that we see that's very close to our MPC behavior here. Now you notice like a little bit of a qualitative difference, and that's an interesting thing. The rewards converged, they're tracked very similarly. Their actual capability seems roughly the same. Qualitatively, the behavior is very different. And so what we did here, if you guys are familiar with T-SNE or UMAP or that kind of thing, we basically did a dimensionality reduction where we look at the state of the robot at a certain time, and we project it to a 2D space, all in the same embedding. The short takeaway is that each of these dots represent a state of the robot, and this big cluster is like the distribution of the 4,000 environments we train with. And let's look at how those states evolve through time. So this gray here is the distribution of states from MPC. This blue cloud is the distribution of states from the randomly initialized RL policy. And here, this orange cloud is the randomly initialized states of the residual controller. Now, what's important is that these remain very close to the MPC because our residual policy is initialized to do nothing. We want to start from our baseline MPC controller that we trust. Let's learn a little bit on top of that. So it makes sense that they're close. But now keep in mind as I play this, these are all subject to the same rewards. So whatever gradient function they follow, it should follow that, like however it does with the algorithm. And this is what we see. So what's really cool is that we see that the RL end-to-end unaffected by this MPC, the RL rewards guided toward this weird cluster over here. Whereas this is very much biased and influenced by the model-based prior that we had before by initializing it. And so I talked about how we're learning like a slight offset, a residual correction to the MPC planner. But I think a different way to think about it is actually warm starting the policy search. From the perspective of RL, we want to start it with a policy that already works well and say, hey, locally search around here to find your best policy that optimizes the rewards. I know what a good controller is. I have 20 years of model-based experience that I don't want to go to waste. So let's try and use that somehow. And that's kind of the motivation for this as well. Yeah. And so some interesting things we can see is that our MPC with slightly bumpy terrain quickly fails. It's, on model ground. Our residual was robust to this. It was never seen in training. I trained it only on flat ground under the most standard, like baseline conditions I can. One thing here, if I can replay that, let's see, can I replay that? Oh, I'm going the other way. There we go. So I'll just point this out when it happens. I should have set this to loop. The residual MPC actually cannot cross terrain that is a certain step height. It gets its foot caught here. This does its own thing, but it gets its foot caught here. Oh, that's tough, right? What do we do about that? My MPC controller is parameterized based on the height of the swing. I can ask it post-training to step a little bit higher, and that's what I do. And it can still adapt online to that. And now let's see if it can cross that terrain. Yes, it can. So that's an interesting finding. It can adapt to the MPC parameters post-training, even though it was never experienced those changes in parameters during training. And now let's take a look at the bottom video. The same thing happens for context generalization. This is our nominal gate schedule. I now post-training modify the context schedule to have a double stance phase, and it doesn't freak out. Like I don't know if I could tune the MPC to do this quite as consistently. To really try and stretch this, we also added a slight flight phase, and it's still capable of that as well. Not for very long. If I extend this, it quickly fails. Yeah.
So I have a question about like, so generalizing to new type of context sequence.
Yes.
Higher swing height. Can you do that with only MPC, or you couldn't do that? So that's why I do it. And then with the residual RL, generalize to more big loss parameters. Yeah.
Yeah, so the comment was basically, am I making the claim that I can generalize this with the residual policy, the changes to these parameters?
What happened to like changing this parameter with the beats? Now I need to something.
Oh, I didn't show here, but generally it fails, or I have to tune it more to make it work. Yeah, the higher swing height will induce larger contacts, larger impulses, and the MPC is not quite as stable. And I'm sure I could tune it to get it to a point where it could cover that case, but I don't want to emphasize tuning too much. Let's try and not tune as crazily as we often have to for.
So what is the output of the MPC? Is it ground reaction forces?
No, the MPC is a kinodynamic MPC. So it outputs ground reaction forces, Q trajectory, and Q dot trajectory. I then map that to torques with the inverse dynamics.
Then the same set of parameters for your RL does. So it's just you set the MPC plus RL. Kind of, have this parallel architecture.
Yeah.
Sum them together. Right?
Literally sum them together. I do the same standard RL law where you have joint set points, and then I just smash the torques together.
The RL training from the beginning, it's going to be stable.
You can't guarantee it's stable, but you can really help it by just initializing all the weights to 0 of the residual policy. That way, yeah, like you'll have some noise on your, it's a randomly sampled stochastic policy, so you have some torque noise, but if you initialize it to be small, like the original residual policy paper from Leslie Cabling at MIT, they did the same architecture where they initialized the weights of the policy to be 0 of the residual policy, and they had some pre-trained like expert policy that they learned on top of. Simply initializing the weights works pretty well, and it can quickly learn to adjust its thing. Yeah, because you don't need the outputs to be big originally. Also scaling the action scale. Scaling the policy output can really help as well. Yeah, just multiply it by a scalar factor like 0.1 for the policy. And you could have curriculum where that gets bigger. I don't find that necessary. I just initialize it to be small and it can learn to adjust. Cool. The other point I wanted to make is kind of from the perspective of, I'm a model-based guy. How can I leverage learning? So is this a video? No, it's not. I thought it was. Okay, whatever. So one thing that I wanted to show here, if the video was playing, it is a video, I'm sure it is. There we go. Is MPC actually has this behavior. I don't have any self-collision constraints on MPC. And you notice that when it's turning, I found this interesting case where I could make it spin and have its knees knocked together. it was still stable, so it could keep turning, but you can see here, this is the penalty for having self-collision. And with the MPC RO, every time it turns, it hits the knees together. One thing that's very hard from a model-based perspective is something like self-collision. It's a very geometric, kinematically weird thing to do. And there are heuristic things that people have done, like add spheres to the knees and keep them a certain distance apart. But to not rely on that, RL is really useful and good at finding non-differentiable rewards and optimizing for them. I can have a reward that says don't hit yourself. And so with the residual policy on the right, it actually never hits itself in the same regime when it's just turning. And we notice it does this by raising its center of mass slightly and adjusting how it steps its foot. Yeah, so that's another cool finding. Yeah, and then here we deploy on a hardware. This was mainly just for viability to show like getting the two of them working together, which was a huge pain. Like getting the MPC controller running alone is difficult. And then you have to add the RL and, sim to real and all this stuff. But yeah, so we showed some pretty basic results that are a little bit scary. But yeah, we just wanted to validate that like, hey, these two can work together and produce stable locomotion on our hardware. And like I said, every time this breaks, we fix it ourselves. So it's good to be gentle with this. Yeah. Cool. So I just wanted to wrap up there. I have a lot of other details and additional results from that work that we could talk about, but just high level, that's kind of the direction of this talk that we wanted to give. We made this tool for GPU parallelization and thought about how can we leverage this for control and learning and structuring learning in a model-based setting for humanoid locomotion. And so Hojay talked really nicely about how we can use model-based quantities, like a well-informed centroidal angular momentum is much better at guiding behavior than something very, very overtuned and specified about where your arm should be or your base angular velocity. And I showed a little bit about how we can use a model-based prior controller to try and guide learning overall. Yeah. So that's the conclusion of our talk. Thank you so much. If you have any questions, please let us know. But yeah. Yeah, questions.
I always wonder people trying to use the IO to trap the model-based controller. So residual MPC is definitely one way. The other way is you can just directly use the IO to trap the
Dagger or BC or some
directly trap the motion on the model-based controller.
Yeah.
I just wonder have you compare these two how
That's a good question.
how's the performance on the hardware really varies between these two?
Yeah, that's a good question. So the question was basically have you considered, behavior cloning, Dagger, these kind of approaches to copy the MPC solutions? I did not do that direct comparison because in my opinion, MPC is not it's not a perfect prior. We don't want MPC to be the thing we copy from because it's based on a lot of assumptions that aren't true. For example, in our MPC trajectory, I showed the video of it walking and having the predictions go forward. The desired path for that MPC controller is literally just this position copy pasted along the horizon. We don't have a good sense of how to design an MPC controller prior that's correct in a sense. That's where I think, if we want to discuss future work, imitating trajectories and having MPC be a guided prior for trajectories that are correct, which in this case might be humanoid-looking trajectories from reference data. I think that could be the direction to go. But directly copying MPC, it's well, if the upper bar is MPC, I already have that controller. So yeah, that's what I was thinking. Yeah, but thank you for the question. Oh, yes.
I think it's for me.
Yes.
Yes, so I'll just read it. So is this approach applicable to the running case with aerial phase? The CAM will be harder to regulate, I guess. So in this work, we specify the context schedule to be always in context. We don't really have the aerial phase. To do that, we need to design the context schedule reward again. And I think if you do that, I think it's also applicable for the running as well. Although it's the arm motion will be much bigger and wider than the running, with the walking cases. But I think it's still applicable if you design the aerial phase. I hope that answers.
Thanks.
Thanks.
Yes. I can say a little bit. These question. We actually use different centroidal momentum transportation, and then we study. It's purely model-based work. We try to do the backfeed that regulates the centroidal momentum dynamics. Yes. This is like the ADMM type of program. I'm not sure you've heard of this. Yes. Distributed trajectory optimization. Yes. It was very hard to converge and the centroidal momentum. So we use some called equal momentum ellipsoid to have different ways to parameterize the inertial tensor. But it's still hard. We just the numerical optimization really work very well.
Yeah.
maybe it's two agile motions. So it sort of didn't go anywhere, like published. So
Yeah.
I guess Z is just curious if your approach can do more agile motions.
Yes, so the inspiration that I try to get from this for this paper from the human motion is mainly for locomotion, like a running and jumping, like running and walking, where we swing the arms like out of phase. But for like backflip, we don't really like swing our arm. Like we try to generate like some momentum forward to go back. So we cannot really use the out of phase reward. But if we know the momentum profile of the agile motion and we use that trajectory as a guidance, I think it also helps. But I'm not sure if we can like achieve that like highly agile motion like off the book.
Yeah. I think that also some directions towards that could be, imitation style. If you have some offline generated trajectory, whether it's from a model-based approach or not, initializing the robot in the middle of that trajectory, I feel like really helps accelerate convergence. That's kind of deep mimic, beyond mimic style training. I've also seen a couple papers using what in our lab we called like the God force, where you have some sort of assistive force that's unrealistic and you curriculum wean that away slowly so that it learns to be able to perform that motion without it. With respect to the optimization, I feel like ADMM, so actually, what the heck? Where's my mouse? Let's see here. So we actually use OSQP, which is, it's ADMM-based QP solver to try and get our MPC trajectory. That's how we solve it. I think just empirically, I've found that ADMM is good for fast, inaccurate solutions, but for highly dynamic motions, I think it's much better to use interior point or penalty-based methods. They just, those constraints are so much more important when you're at the limits of your dynamics that it may be interesting to try. I remember my first work was about landing, where I had like very nasty contact implicit constraints, and I had to resort to using K-nitro, which is like IP-opt on steroids. It's like so good at nonlinear problems, but it's also, expensive, closed source, all that stuff to get those solutions. Yeah, but just something to think about. Yeah, question, please.
Good talk.
Thank you.
So I just have like a question. What do you think is like the most challenging things like during the MPC video, right? Or like for example, currently, it's like you mainly consider about locomotion. How scalable it is to scale this framework to like some more like a content-rich local manipulation tasks?
Yeah, that's a great question. So the question was about how, basically, let's scale this up to something more complex than just planar locomotion. I think that's a good point. And I don't think that this is the correct architecture or correct solution just going forwards for, future robotics type stuff. And it's kind of always a internal struggle for me as a roboticist about, there's like VLA self-attention soup where you kind of just all your embeddings and your tokens are mixed together and somehow it learns something reasonable out of it. And I don't think, I don't want to give the impression that that's like, dumb or silly. I think it's working amazing and doing like crazy things. But on the other hand, I'm kind of taking the opposite approach where let's start from the opposite of soup, like very discrete ingredients and slowly build on top of that so we can clearly look at what our torques are doing. I think in terms of scalability, the direction that I want to go in is trying to leverage this kind of MPC, but not in such a separate way where I directly add these torques together. But rather, now that I have this architecture and this parallelization set up, can I now incorporate diffusion or imitation into this loop? Can I now feed the torques of the MPC into a lower level policy that can then make these really robust and that kind of thing? But let's have the biggest problem I see with scaling up with purely data-driven methods is always generality. And how do you make sure that your training is data agnostic? That if you get a trajectory or desired task that's completely out of distribution, how can you still reliably track that task? For example, you have your unit trees that learn to walk across the stage, but if I ask that, can any of them, and can that policy walk with one arm held out? That is something that should be trivial for anyone who's learned how to walk to do, but it probably can't do that because it's not in data. But it should be able to do that. And that's where I think having some sort of like higher level model-based planner whose trajectory and desired torques are fed into something lower level is the direction I want to go going forwards if I were to continue doing this kind of research. Yeah. I think something interesting, which maybe I'll show a little bit here, is one nice thing about having these torques just smashed together is we can look very directly at what the residual torques are doing and what the policy is learning. So this is an example of what's the metric I have here? So yeah, the ratio of torque magnitudes, how much is the policy torque being output versus the MPC torque? And this is over velocity commands. So we already see some asymmetry. Like we use the residual torque more when we're moving forwards and less when we're moving backwards for the MPC plus residual policy. This is actually something we noticed for a pure MPC controller too. It's really good at walking backwards, more so than walking forwards. It can like move faster backwards, which is interesting to see here. And we have this kind of like, I don't know, symmetric across this diagonal for the angular velocities, which is just interesting to look at. This is a similar thing where we actually look at that same residual, or sorry, same ratio over the contact phase. So at 0.5, we have this contact switch. And so what we see is like, oh, like we're trying to use more residual torque, more, the policy is activating more right before contact, and then it follows the MPC again. And like in a similar way, we look at the cosine similarity. How aligned are the vectors of the torque from the residual policy, like the 18-dimensional, we have 18 motors, 18-dimensional torque versus the 18-dimensional vector from MPC. How aligned are these, like throughout the training process, throughout contact? What we actually notice is that, oh, right before contact, they're almost opposite. Like the residual policy learns to oppose the MPC torques entirely. And so I think that's what explains it, being able to do these kind of heel-to-toe transitions and be more robust over the surface. It fights the MPC because it learns how to adjust to that. Yeah. So, you know, with these results, like that's how I kind of want to go forwards, slowly scaling up and building up on our currently established architecture. Yeah. Yeah, question.
I have one question. I'm just curious about if you guys have any plans to incorporate perception into this, because I think you could very well just like take your blind MPC and like warm start your training with that, and then online use perception to augment the MPC side. Training with perception MPC is interesting as well. But yeah, I'm just curious if you guys have any thoughts.
Oh man, that's a great question. And Hoja and I, we can both speak to this, I think. I think Songbei has been trying to get a vision guy in our lab for a long time. And no one really wants to join our lab to do vision because we do like low-level controls, basically. So I think, and he, one thing we talked about last group meeting was about, I think, like a very important future direction is how exactly we incorporate perception into a robotics control stack. You have the VLA soup, you have like classical methods, like somewhere in between maybe is the direction. I think everything we've done is blind, and our humanoid has like a little LiDAR in the base, but we've never used it. We've never even turned it on, actually. And that's something we definitely want to work on going forwards. It's just, we need the right guy to do it and the motivation to do it. And yeah, maybe Hoji.
Yeah. I mean, I agree with Jeon. The main reason we didn't do is that we just didn't have a person doing it. But I really do agree that like if we want to go beyond the just flat train or just simple step, we definitely need the perceptions and how to process the perception, because like extremely high dimensions. And also like nowadays the humanoids are moving from just locomotion to local manipulations to observe where the object you want to interact with. Locomotion is basically like avoiding the environment, whereas the local manipulation is actively interacting with the objects with the environment. So in that sense, I think the perceptive local manipulation is very important, and I think that's what we are planning to do.
We're always planning to do it. Yeah.
We finally have one person working on the perception as a postdoc. So hopefully next project will be the combination of that.
Yeah.
Okay, all right.
Okay.
Great. Yeah. Thank you guys so much.
Thank you.
Stand next to some